And uh, for today, our purpose is to compare auto, diesel, and dual cycles. If I ask you the question, what are the various processes in auto cycle? So the processes in auto cycle, the first one is the reversible adiabatic compression, followed by heat supply at constant volume, followed by reversible adiabatic expansion, followed by heat rejection at constant volume. So basically, there are two reversible adiabatic processes and there are two constant volume processes in case of Otto cycle. Okay, if I take a diesel cycle, then two reversible adiabatic processes would be there. Along with that, we will have one change here. We will have heat supply at constant pressure. That will be the third process, and the fourth process will be at constant volume during which the heat rejection is taking place. So this one and these two constitute a diesel cycle. I think somebody wants to join, so just wait for a second. uh, yeah, this is really ridiculous. Okay, then finally we have the dual cycle, and we know in case of dual cycle we have heat supply at constant volume as well as constant pressure. So basically, I would say that the first process is number one is reversible adiabatic, followed by heat supply at constant volume, followed by heat supply at constant pressure, followed by reversible adiabatic process, followed by heat rejection at constant volume. So there are five processes in case of a dual cycle. Now, when I say I had to compare this auto, diesel, and dual cycle, so I should have some common parameter corresponding to which I can compare these three cycles actually. So the those parameters could be, the first one is it could be the same compression ratio or it could be the same amount of the maximum pressure and temperature. So the first case which we are going to consider is the comparison of auto, diesel, and dual cycles for same compression ratio. You know that the compression ratio is given by RC and it is equal to V1 by V2. And I have already told you that this V1 is equal to VC, which is the clearance volume, plus Vs, which is the stroke volume, divided by V2. V2 is nothing but the clearance volume. So this is the value of RC. And I have told you that the value of RC, if it is a petrol engine auto cycle, the value is somewhere between 9 to 10.5. Somebody is talking actually. Please stop talking or mute yourself. Who is talking? Ritik Solanki.
तो जैसे कि हम देख सकते हैं,
Ritik, can you Abhinav, please mute your mic. Okay, so when I say uh, diesel cycle, then the value of RC varies between 14 to 22. Okay, so these are some values, but now what we are considering is we want to compare these three cycles for the same compression ratio, means the value of RC is fixed. So naturally, if I take the PV diagram, if this is the initial state here, point number one, and this is the final state here, point number two. So it means I am fixing these two states. Okay, these are the two states which I am going to fix. And then naturally, you can understand that when 1 and 2 is fixed, automatically the point number 5 which is shown here will be fixed, and we will discuss about it why it is fixed. And the reason, if I would like to tell, is that this process is at constant volume, and this is common in all three cycles actually, and it's going to remain fixed. But our purpose here is to draw the TS diagram and not the PV diagram, because though we can represent all three cycles on the PV diagram, but TS diagram is a better way to understand how we are going to draw these three cycles for the same compression ratio. So you can see this diagram, TS diagram, on the left side, which is drawn here. So uh, we have first of all two constant volume processes or two lines which are representing the constant volumes that are shown here. This is V is equal to constant, and this is another V is equal to constant. These are the two constant volume lines. Probably I will take the next slide and explain you, then I will come back to this slide and you can see it. So let us go to a blank slide here. So just a minute, I will change the color. So let us see, this is the TS diagram which I am going to draw here. Okay, and I have chosen two constant pressure, two constant volume lines. This is, you can say, this represents V1, this represents V2, and both these are considered as constant along these curves. If I choose this as the initial state point, point number 1 here, okay, and now the first thing is that I am going to draw the constant volume cycle or the Otto cycle. So the first process is reversible adiabatic compression, and during which there is no heat transfer. So this is the process which is shown here. You know, I can always write that delta Q is equal to TDS, and during this process this value will be equal to 0, or I will say that ds is equal to delta Q divided by T. Since delta Q is equal to 0, so change in entropy will be equal to 0, or I can say S2 is equal to S1. So that is why it is a vertical line on the TS diagram. The second process is at constant volume, and during this process we supply the heat at constant volume. So this is point number 3. So I am considering that the heat supply is going up to point number 3, and then it is followed by the reversible adiabatic expansion, during which once again the entropy will remain constant, and we will come to state point number 4. Okay, finally we will be coming back to the initial state point, which is state point number 1 in this case. So this is the heat rejection process at constant volume. So I hope this is clear to you. No, actually, as I told, that we are considering that the compression ratio is constant. Okay, that is V1 by V2 is constant. So it means for all three cycles the volume V1 and V2 will be same. So let me now draw the diesel cycle actually. So once again I will not change point number 1 and point number 2. So the process 1 to 2 is same as drawn earlier for the Otto cycle. Now you remember that in case of diesel cycle, the next process is heat supplied at constant pressure. So from point number 2 I will have to draw a constant pressure line. So I am going to draw the constant pressure line something like this. Okay, so this is a constant pressure line. So during this the pressure remains constant, and I am going to terminate it at this particular point. Okay, I think there is one more thing here also. uh, yes, one more thing I would like to add here, that when I am considering comparison of Otto, diesel and dual cycle for the same compression ratio, you should also consider one more point, that there is same heat rejected also. Okay, there is same heat rejected, so this has been missed here. So the first case is comparison of Otto, diesel and dual cycles for the same compression ratio and same heat rejected. So when I finish my process at this particular point, let us call this point as point number 5. I go to point number 4 once again, following the process from 5 to 4. Okay, and this is the reversible adiabatic expansion, during which the entropy remains constant. When I say reversible adiabatic expansion, it is basically the power stroke of the 4-stroke engine, or say 2-stroke engine. We haven't discussed about 2 strokes engine, but the process is that of the power. Then 4 to 1, it is the heat rejection at constant volume. So basically I can say this is the cycle 1 2 5 4 1. This is the diesel cycle, and the Otto cycle was 1 2 3 4 and 1. I hope both the cycles are clear to you. uh, And the reason now you can understand that because we are supplying, we are rejecting the same amount of the heat. That is why this point number 4 is also somehow fixed actually. So basically in this case, point number 1, 2 and 4 gets fixed. Now let us move to the dual cycle. Now dual cycle, I will take once again the change the color. Once again, point number 1, 2 and 4 are fixed. So I'm not going to touch those. So 1 is same, 2 is same, 4 is same. But when we reach at point number 2, what we have to do after the compression process, the in case of dual cycle, first we have to supply heat at constant volume, and then we are going to supply the heat at constant pressure. So you can see the constant volume process is shown here. I can say go up to say this particular point. It is means my choice, up to which point I can go for heat supply at constant volume. Okay, so this is constant volume. Let us say this is point number 6, and it is followed by heat supply at constant pressure. So the slope would be different. So I will be following this curve now, where the this process is constant pressure process. This is P is equal to constant. And finally, I reach up to this particular point, and this particular point is named as 7. This point was actually point number 5. Okay. And then from 7 to 4, it is the reversible adiabatic expansion. It's the power stroke. And then from 4 to 1, it is the heat rejected. Okay, at constant volume. So I hope the three cycles are clear to you. And does anybody have any question about this TS diagram? If you have any question, you can ask. Okay, it seems it's clear to you. So once again, let me see this diagram. You can see this particular diagram, TS diagram, which you can, it's more clear than what I have drawn here. So you can see it. This is point number 1 here. This is point number 2. And if I am going for the auto cycle, it is 1, 2, then point number 6, then point number 5. See, I have chosen different state points, and this diagram which I have taken from the book, they have the different state points. So auto cycle is 1, 2, 6, 5, 1. Whereas if I talk about the diesel cycle, then it is point number 1, point number 2, point number 7. This is the constant pressure process, followed by 7 to 5 and then 5 to 1. And similarly, if I talk about the dual cycle, it will be 1 to 2, 2 to 3 up to this particular point, followed by 3 to 4, which is the constant pressure process here, and then from 4 to 5 and 4 to, and then from 5 to 1. This is how we have drawn this cycle actually. Now I would like to ask one more question. We have discussed about it. If I am drawing a TS diagram like this, and if this is the curve from 1 to 2, what does it shows? This shows the change in entropy. Means, yeah. Anybody would like to tell?
Sir, the entropy is increasing
Okay,
as we go from state point 1 to state point 2.
correct. And what else is there? What is the area under this curve representing this area?
Sir, the heat is absorbed by the system.
It
Heat
is the heat.
supplied to the
Yeah,
system.
heat is the heat.
Released.
It is the heat supplied. Okay, you are correct. And suppose if I would have been going in the say like this, say from this particular point, this is point number 3, and I follow this path and I go up to this particular point, say point number 4. What does it shows?
The
Heat
heat is released.
rejected.
It shows heat rejected, and this area which is under this curve, it shows it is the heat rejected part. And you know that W, the network is given by heat supplied minus heat rejected. Okay, so naturally the area which is left, which is the area which is left, this is the area which is left here. So this represents the network output of the cycle. So this is what you need to remember. And then let us move, and now we can discuss what will happen in this particular case. One more thing I would like to tell you, when I say I have to compare auto, diesel and dual cycles for same compression ratio and same heat rejected, my purpose is to compare three parameters. First one is, let us say, heat supplied. Second one could be heat rejected. the third could be network output, and fourth is efficiency. So these are the four parameters which I have to discuss when I am giving a particular statement for the comparison. Okay, so let us see. Now this is the diagram which I have taken once again. So I have written here the cycle 12651. So what is 12651? This is 12651. So it's basically auto cycle. Similarly, we have diesel cycle which is given by 12751. So 1, 2, 7, 5 and 1. And then dual cycle, it is 1, 2, 3, 4, 5, 1. So it is shown here. This is 1, this is 2, this is 3, this is 4, and this is 5, and followed by 1. Okay, so we know about it, and we have also discussed how we are going to calculate the heat supplied and heat rejected. So as I said, that in this particular case we have considered that the compression ratio is same and the heat rejected is same. So let us first of all calculate the heat rejected. And in all these processes, all these cycles, that is auto, diesel, and dual cycle, the one process during which the heat rejection is taking place is common, and that process is 5 to 1. Okay, this is the point, and this is the point. So this is the process actually from 5 to 1. And we have just discussed the area under this curve will represents the heat rejected. So this part is actually heat rejected. Okay, and it is same in all three cases. So I can write here heat rejected is equal to area under the curve 5 to 1, or I can say QR, which is representing the heat rejected, is area 1 5 B A 1. Basically it is the yellow part which I have shown. So I think it's very visible here in the diagram. Okay, and now what I can do is I can calculate the heat supply. So first of all, I am taking the heat supply in case of diesel engine. So heat supply in case of diesel engine, let us see. So which is the process during which the heat is supplied in case of diesel engine? Heat is supplied in at constant pressure, and this is the constant pressure process here from 2 to 7. Okay, this is the point here, and this is the point here. So whatever is the area under this curve 2 to 7, that will represent the heat supply in the diesel engine. So I can see here clearly that it is the red area and the yellow areas which is representing the heat supply in case of diesel engine. So I can say easily that area A21 to 275BA. So you can read the numbers here. I have written this point as A, this point as B. Okay, this is A here. So A1275BA. Okay, so this is the heat supply in case of diesel cycle. Similarly, if I go for dual cycle, then so the dual cycle, in case of dual cycle, the heat is supplied between the process 2 to 3 and 3 to 4 actually. Okay, I have drawn it here. So you can see there is addition of green area in it in addition to yellow and red areas. So I can say the heat supplied in case of dual cycle is green plus red plus yellow areas, and it is equal to area A12345BA. Okay, so once this is known, we can go for the heat supply in case of petrol engine or the auto cycle. And you can see there is some additional area which is represented here by the blue color. So the heat supplied is blue color plus green color plus red plus yellow. These are the areas, and the total area is A1265BA. So that is the area, and it's visible here. The area in the auto cycle is the maximum. So it means the heat supplied is maximum in case of the auto cycle, and it is least in case of constant pressure process, means for diesel cycle. Okay, so I can write here that QS for the auto cycle is more than heat supplied in case of dual cycle, is more than heat supplied in the diesel cycle. So I hope this is clear to you. So here I have written, use the nomenclature heat supplied for the auto, heat supplied for the dual, and heat supplied for the diesels. And which is the highest one. Now let us focus here. This is the formula for the efficiency. It is given as 1 minus QR divided by QS. This is the heat rejected part, and this is the heat supplied part. Now you tell me, what about this heat rejected? This heat rejected is actually constant in each and every case. So in this expression, if I take this particular fraction here, the numerator is constant. If I choose the Otto cycle, let us say, then you know that heat supplied is maximum in its particular case. So the fraction which is shown here will be minimum here, and 1 minus minimum is maximum. So it is understandable that the efficiency of the Otto cycle will be maximum, and in the second case it will be the efficiency of the dual cycle, and third it will be the efficiency of the diesel cycle. So basically we have compared three parameters. We have compared heat supplied, heat rejected, efficiency. Now we want to compare the work output. Now work can be calculated by two methods. One could be I use the formula efficiency is given by W net divided by heat supplied, and which cycle has the highest efficiency? The Otto cycle has the highest efficiency, and the heat supplied for the Otto cycle is also maximum. So W net or W for the Otto cycle will be maximum, and it will be followed by dual cycle and followed by diesel cycle. So I have written it here. W for Otto is maximum, followed by dual, followed by diesel. Not only that, we could have calculated this value from the areas also. We know that W is given as heat supplied minus heat rejected. Now this parameter is constant. Heat rejected is constant in all the cases, and heat supplied is maximum in case of Otto cycle. So we can utilize this equation and find out for which case the work is maximum, and it's once again will give the same answer that the work in case of Otto cycle is maximum, followed by dual, followed by diesel. Is it clear to you?
Sir, I have a doubt.
Yes, tell me.
Sir, how do we know that the curve 2 to 7, that is P is constant, is below the P is constant curve?
Did you attend the previous class?
Yes, sir.
I have told it there. We defined, we discussed about the slope of the two processes. I can show you. Just wait for a minute. If you don't remember exactly, I will show you. Yes, this is the topic which I discussed, and I have shown it here why the slope of the constant pressure is lower in comparison to the slope of the constant volume. If you have not understood this, you won't be able to get the idea there. So you have to go
Okay,
through the
sir. Yes.
previous. You got it?
Yes, sir. याद आ गया. Yes,
याद
sir.
आ गया. Good, good. Okay. So let us proceed further. So we have compared the Otto, diesel, and dual cycles for the same compression ratio. Now we are going for the next case. We are going to compare the Otto, diesel, and dual cycles for the same maximum pressure and temperature. Okay. So same maximum pressure and temperature. We want to compare these two. Okay. So once again, we have to go slowly and understand how we can draw these cycles. So I will be drawing it here only. Okay, so let us see it here. This is once again the TS diagram, and once again I can start with the Otto cycle. This is the, you can say, constant volume lines here. This is you can say V2, let us call it as V1, and now we are given with a particular condition, same maximum pressure and temperature. So there is no restriction on the compression ratio here. Okay, so the compression ratio can change actually, but yes, in this cycle the maximum pressure and maximum temperature are fixed. So if you see on the in the right side diagram, PV diagram here, so if I take let us say Otto cycle, okay, in which there is a constant volume process. So you can see here This is point number 1, this is point number 2, then this is the heat supply at constant volume. So we go up to point number 3, and then I think there is some mistake here. Yes, the next process should have been I think the diagram is the previous diagram. Let me check. Or maybe there is some problem in the diagram. Okay, maybe some other diagram I might have used. So actually from point number 3 we will have to go for the reversible adiabatic compression. Okay, this doesn't seem to be correct. Okay, so I will discuss about it later on. Let me talk about the TS diagram first of all, and you would be able to understand it easily. Just wait a minute. Okay, so I am going to draw the Otto cycle. This is process 1 to 2. Okay, this is reversible adiabatic compression, and during this the entropy will remain constant, followed by heat supplied at constant volume. Let us consider that this is point number 3, and then we have the reversible adiabatic expansion for the Otto cycle. So this is point number 4, and 4 to 1 is the heat rejection at constant volume. So this is the first cycle, Otto cycle we have drawn. Now you can see I am considering this cycle only, and I say the maximum temperature. Yes, this is the maximum temperature in this cycle. So this is fixed. So I will say this is going to be remain fixed for other cycles also. And then the maximum pressure. So see, at point number 3 right now you can't see the constant pressure line, so I have to draw it here. So let us say, because the slope of the constant pressure line is lower, so this is the constant pressure line actually, and I will say that this point will be fixed. Okay, this would have been drawn a little bit up, so just a second, give me a minute. Okay, so this is the constant pressure line, and its slope is lower in comparison to constant volume line, which is shown here. Okay, now let us take the second cycle, which is actually the constant pressure cycle or the diesel cycle. And in that particular case, the second process of heat supply takes place at constant pressure. Now point number 3 is fixed. आपको पता है point number 3 fixed है. So how to get the point number 2 of that particular cycle, or I can say that is point number 5 after the compression. So I say that the diesel cycle is 1, 5, 3, 4 and 1. So basically I know that process 3 to 4 is already with me, process 4 to 1 is already with me, and process 5 to 3 and 1 to 5, these are the two missing processes of the diesel cycle. Okay, and 1 to 5 is basically compression process. So how to get this point number 5? I can extend this constant pressure line backwards here. Okay, and I can move upwards here, and I will get the point number 5 here. Okay, this is point number 5. So that is how I can draw the diesel cycle. So this is constant pressure. So this is the heat supply at constant pressure. I hope this is clear to you. And then the whole cycle is clear to you actually. 1, 5, 3, 4, 1. Okay. Now let us talk about the dual cycle actually. We have to draw on the same TS diagram. So let me change the color. So I will take green color now. Okay, so what is the first process? It is the reversible adiabatic compression. And once again, when I am talking about the dual cycle, once again, this point number 3 is going to remain fixed. Okay, this will be fixed. So I have circled it. Point number 4 is fixed, circled it. Point number 1 is fixed. So I will call this cycle as 1, 6, 7, 3, 4, 1. Okay, so now first of all I have to see where is the point number 6. Point number 3 is fixed, so we have to backtrack actually from the point number 3. So if I come backwards in case of dual cycle from point number 3, it is the process of heat supply actually, and it takes place at constant pressure only. Okay, so I can say that this is the point number 7. Okay, and this is the constant pressure process in case of dual cycle, which is taking place for the heat supply. And before it, we have the heat supply process which is taking place at constant volume. Okay, so I will once again backtrack, and I will draw a curve which is representing the constant volume process here, because its slope is larger, so it is going something like this. Okay, so this is 2 to 7, and this is the heat supply at constant volume in case of dual cycle. And one thing I would like to tell you here, that we have arbitrarily chosen the point number 7. Okay, so it's up to us. Okay, uh, and because we have to compare these three cases, these three cycles for the same maximum pressure and maximum temperature. Okay, so I can choose point number 7 and point number 2 as per my choice, but yes, there should be both the processes of heat transfer, which is constant volume as well as constant pressure. Okay, so it means the point number 2, sorry, not point number 2, I am wrong here. This is point number 6 here, point number 6 rather. Point number 2 was here. Okay, so I'm sorry for the mistake. So basically 1 to 6 is the reversible adiabatic compression in case of dual cycle. 6 to 7 is the heat supplied at constant volume, and then from 7 to 3 it is the heat supplied at constant pressure. Okay, once again, point number 6 will always lie between point number 2 and 5, and 7 will lie on the constant pressure line 3 to 5, and somewhere in between. It depends how we choose 2 and 7 actually. Okay, is it clear to you? Any questions on this? If you don't have any questions, I will proceed to the explanation part of it. Once again, if you see here, we have three cycles. You can see here. Now the numbering is different here, but I have explained you how to draw them. So the cycles are 1, 6, 4, 5, 1. So just see it carefully in the diagram. 1, 6, 4, 5, 1. This is basically Otto cycle. Okay, because the heat is supplied at constant volume. Let us move to the next one. 1, 2, 3, 4, 5, 1. 1, 2, 3, 4, 5, 1. This is the dual cycle. You can see here in the diagram. Okay, then you can go for 1, 7, 4, 5, 1. This is the diesel cycle. So you can see these points in this diagram here. If this is clear, I can proceed with the same way I have done for this in the previous case. So first of all, I am calculating the heat rejected. I say this is QR, and what is this area of heat rejection? This is the blue lines or the blue area. Okay, blue area, and it is area A15BA. Okay, this is the area. So I know which area represents the heat rejected. Then I go for the Otto cycle heat supply, and what I can see is it's just the green area plus the blue area which represents the heat supply in case of Otto cycle, and it is the area A1645BA. You can just see it carefully. A1645BA. So this whole area, okay, and the blue area under it, that is the heat supplied in Otto cycle. Then we can go for dual cycle. In case of dual cycle, we have green area plus blue area plus red area. This represents the heat supply in case of dual cycle. You can note down the numbers. Area is A123455BA. Then we can go for diesel cycle heat supply. So we have to just add the yellow area in the area of the dual cycle. So blue area plus green area plus red area plus yellow area. Okay, so this is actually area A162735BA. That is the area. And now we know in which case the area is maximum for the heat supply. You can see the topmost cycle is the diesel cycle. So heat supplied or the area is the maximum for heat supply in case of diesel cycle. It is followed by the dual cycle, followed by the Otto cycle. Okay, so uh, this is you can say, it means if I calculate the efficiency here, which is given by 1 minus heat rejected divided by the heat supplied. So heat rejected is once again same in all three cases, and heat supplied is different. Heat supplied in diesel cycle is maximum, so the efficiency of the diesel cycle will be more, followed by the dual cycle, followed by the Otto cycle. Then you can, in a similar manner, you can write the expression for the work. So because the efficiency of the diesel cycle is maximum, so its work is going to be maximum, followed by the dual cycle, followed by the Otto cycle. So this is how we can go about it. Okay, is it clear to you? Any questions on this? Okay, so if it is, there is no question, I'm not going to explain you about these examples actually, though I have shown it here. When I will be uploading the video, you can read them. If you have any doubt about this, then you can ask me. I think you should not have any doubt about this. This is quite easy. I have taken these examples from the PK Knox book only. This is the, I think, another question. Some slide has been uh, changed actually. I think this might have been the question. So I have solved it here also. This is the next question. Okay. So I think these are initial questions of the PK Knox book on auto, diesel, and dual cycle. So now what I am going to do is I'm going to discuss one more similar case where I am saying that uh, the compression ratio in all three cycles is same. Okay, this is same for all three cycles, and let us say that heat supplied is also same in all three cycles actually. Okay, so that is the question. So I am giving you 5 minutes. You can try it yourself and draw these cycles actually. So this is a sort of mm, question for you. Okay, so I will join you after 5 minutes, and then I will discuss about it. In the meantime, I will unshare my screen, and I will do it myself. So you do it. So I have started drawing the diagram. First of all, you should go for Otto cycle actually. So draw the Otto cycle as you have been drawing in the previous cases. Make two constant volume lines on TS diagram. So once you have drawn these lines, you can go for plotting the processes. Let us say the Otto cycle is represented by 1 to 2 reversible adiabatic compression, then 2 to 3 is the heat supply at constant volume, followed by power stroke or reversible adiabatic expansion from 3 to 4, and 4 to 1 is the heat rejection at constant volume. Okay, so the Otto cycle is given by cycle number 1, 2, 3, 4, 1. 1, 2, 3, 4, 1. I have written it here. Okay, now I will go for diesel cycle. Okay, I have said the compression ratio is same, so the point number 1 will be fixed. Point number 2 will also be fixed. Okay, but other 2 points won't be fixed, so I'm going to make it, but I am not explaining it right now. So now I am going to draw the constant pressure process, constant pressure heat supplied. It is process 2 to 4 followed by process no, so not 2 to 4, it is, let us say, it is 2 to 5 actually. Okay, so this is a sort of hint for you also. It is process 2 to 5 followed by process 5 to 6, which is the reversible adiabatic expansion, and then it is process 6 to 1 for the heat rejection. Okay, so the cycle in this particular case is 1 2 5 6 1. So then I am going to draw the dual cycle. Okay, so in case of dual cycle, I have 1 to 2 is fixed, as I have already told you that process 1 to 2 will remain fixed because the compression ratio is same. Then it is the heat supplied at constant volume. So let me say that it is taking place from 2 to 7 followed by heat supplied at constant pressure. So it is point number process from 7 to 8 followed by reversible adiabatic expansion from 8 to 9, and from 9 to 1 it is the heat rejected at constant volume. So I have not shown it to you, but let us see whether you were able to make it or not. So let me write the cycle. It is 1 2 7 8 9 1. Okay, just wait for a second. I will now share my screen with you. If anyone of you have drawn, you can also share your screen. Anyone? Yeah, but for you, because you are not making on the uh, laptop, I can directly write on my screen, so better I would show you. Just wait for a minute. So you can see it here. Can you see the screen? Can you see the screen?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So let us see it here, how I have drawn it. I said that the compression ratio is same. Okay. So compression ratio is same. This is the first thing. Then I said the heat supplied should also be same. So I started with the Otto cycle. First of all, I have drawn two constant volume lines V1 and to represent V1 and V2. So this is 1, 2. I go up to point number 3 here. Okay, and then come to this point number 4. Now I know which areas are representing the heat supplied. You know the area, if I extend this line, say up to here, this is point number A, and let us say this is point number B. So the area which is representing the heat supplied in case of Otto cycle is just a minute, heat supplied Otto is equal to area A 1 2 3 4 1. Is it clear to you? Is it clear?
सर 4B होगा ना?
Yeah, 4B. Yeah, B. Okay, so ये area हो गया हमारे पास. Now when I draw the diesel cycle, you know that point number 1 and 2 are same. Okay, and then the third process is from 2 to 5. This is the constant pressure process. Okay, this is constant pressure process. So you can see here, if I am making the diesel cycle, this area which is shown here will be reduced in comparison to the Otto cycle. Okay, so how to compensate this area? I am compensating this area by extending this line, which is starting from point number 2, during which the heat is supplied at constant pressure. I am extending it up to point number 5. Okay, so by this area, which area? I will just show you, not red color. Let me mark it by light blue. This area. Okay, this is the increase in area, and this area which I have represented here. Okay, this area, this all area. Okay, this is the loss in area for the heat supplied, and this one is the increase in area for the heat supply for diesel cycle. So basically, these two areas are, this is loss wala area, this is loss, and this is gain. These two areas are, I am considering to be equal. So I have gone up to point number 5, and then it is followed by process 5 to 6 and then 6 to 1. So this is the diesel cycle. Then I have to think of dual cycle. So in case of dual cycle, I can go from 2 to 7 like this. Okay, this is the heat supplied at constant volume. But now I have to go for constant pressure heat supply. So I am going along this particular line. I go about up to point number 8 at constant pressure. This is constant pressure line. Earlier it was constant volume line. This was going like this, and this is constant pressure. This is going like this. So there is very less loss of area in comparison to auto cycle, and this is this area. Okay, this area, which is representing the loss in heat supplied in comparison to the auto cycle. Okay, and this has been compensated by this area, this whole area. Okay, so now I can say for all three cases I have made equal areas which are representing the heat supply. But yes, there is some change. That change is in the heat rejection. So can you tell me in which case the heat rejection is minimum?
Sir, auto cycle.
4 to 1.
Auto cycle, it's the minimum, followed by
Sir, followed by dual cycle.
dual, followed by heat rejected in
Diesel.
diesel. Okay, so I hope this part is clear to you. Now I can go for writing the expression for the efficiency. It is equal to 1 minus heat rejected divided by heat supplied. Okay, now this heat supply is constant in all three cases, and this heat rejection is varying. So wherever the heat rejection is minimum, that this value of this fraction will be minimum, then the efficiency will be maximum. So in which case this efficiency is maximum? I think it should be auto cycle, which have the maximum efficiency, because the heat rejected in auto cycle is minimum, isn't it? Followed by efficiency of the dual cycle, followed by the efficiency of the diesel. Is it clear? And then you can go for calculating the work, because the heat supplied is same and the heat rejected is minimum in case of auto cycle. So W for auto cycle will be maximum, followed by W for dual cycle, followed by W for diesel cycle. So is it clear?
Yes, sir.
Okay, so I will end my lecture here. Just wait a minute.